Mr. Vishnoi. I certainly, and I wanted to say hello and good afternoon to all presenters as well as the audience, and thank you for the opportunity. Let me go to my slide deck, and then I will share my screen. Sorry. What happened here? Do you see my presentation deck?
Yes, sir.
Okay, perfect. I'll put it in slide mode. Okay, we're going to talk about liquid air energy storage. And just as Mr. Sen and Mr. Vishnoya stated, one of the, let me see, I'm trying to minimize this. Okay. One of the challenges the world is seeing is the moving to renewable resources. Today in 2020, about 18% of the renewable worldwide power energy comes from renewable and majority from dependable hydro, fossil, and nuclear with inertia. But if you proceed to 2050, over 68%, probably even higher, will go to intermittent solar and with wind, with no inertia. And this is one of the reasons energy storage is going to be very, very important, not only in India, but certainly globally. Because as we all know, renewable power is not available 24 hours a day. And so a lot of work is being done currently on energy storage, certainly on the batteries. And I'm going to talk about using liquefaction of air and regasification of air with the power block, which is known as the liquid air energy storage system. So just real quickly, I think all of you have seen this duck curve, but basically the takeaway from this is if you look at it, the solar power actually produces this curve, the solar PV. And if you look at it, a lot of power is produced during hours where you actually don't need it. So what's happening in today's world's grids is this is getting curtailed because you need the power, as Mr. Sen mentioned, to be available when you need it and ability to shift it. If you look at the bottom three portion of the chart, you have the dependable synchronous power with inertia. This is your thermal plants, the nuclear plants, the combined cycle plants. And then as you get into the undependable synchronous inertia, that middle line is basically the system demand. So at any given time, wind and solar is probably generating a lot more power than is being utilized. And as you shift more and more into renewables, this peak becomes much larger. So hence the requirement for energy storage. So bottom line is you need long duration energy storage, both for energy shifting and ancillary services. So as a company, Sumitomo Heavy Industries acquired Foster Wheeler. That's what the FW comes for. A lot of you may know Foster Wheeler. We were one of the pioneers of boiler technology and power, as well as oil and gas refinery technology very early on. But just like any company, we're also decarbonizing our technology. So Sumitomo Heavy acquired us. And then last year, we put an investment in a company called Highview Power out of UK with an equity position. And Highview has developed this liquid air energy storage, or known as cryo batteries, where they've basically taken the old liquefaction of air, which is an LNG process, and made it a power recovery unit algorithm to basically utilize this liquefaction and gasification of air and running it through an air turbine. So that's basically the process, and I have a little process video to show as I will share with in my slides. So what does this technology do? So here's a very simplified process diagram where you have two segments of the plant. You have a charge and you have a discharge. The charge is this refrigeration unit, and simplified very easily. When you have excess power, we take the excess power and we draw an equivalent amount of atmospheric air. We dry the air and then we compress it. And then we use this Claude process, which is known as the charge system, to basically liquefy the air. As the air is liquefied, we store this in low temperature, very low temperature, low pressure tanks as the energy medium. And then what happens is when we need to discharge it, what we do is we basically regasify this liquid air and back into the power recovery unit. And so what happens in the process is in the first segment, you liquefy the surrounding air, you compress it. During the heat of the compression, we generate a lot of heat. We stored this heat in hot oil or glycol tanks, which is known as a hot store. Similarly, as we use the Claude process to cool this air down to liquid, we generate a lot of cold, and this cold energy is stored in gravel tanks, which is known as a cold store. Why are these two important? In order to increase the cycle efficiency during the regasification process, we utilize the heat to basically heat the liquid air and expand it. And then we utilize the cold store back into the charge station. It's essentially, that's how the system works. And the other key thing about this entire system is these are designed as a plant life of 30 years. There's no capacity decay, no fuel is being fired, and basically it's a fully recyclable plant. We're using air as the medium for energy storage. Obviously, in the process, we take out the CO2 and impurities before we liquefy, because carbon dioxide melts earlier than air, so you don't want that in the system. So that's essentially what the process is. A little bit more detail. So here's what a plant looks like if you look at the schematic. As I mentioned, the charging device uses off-peak electricity to power an industrial liquefier to produce liquid air. The energy store is where the tanks are held. In this case, these are the white tanks, and where the liquid air is stored typically in 30-meter high tanks. And these tanks can be sized to recover about a gigawatt's worth of energy on liquefied air. So just to give you an example, about 700 liters of atmospheric air converts to about 1 liter of liquid air. So essentially quite a bit of air is stored in these liquefied tanks. And then if you know the gas volume conversion, when you are taking liquid air and converting it back to gas, you're expanding it by almost 700%. So what we do is during the expansion process, we use cryogenic pumps to not only expand the liquid air into gas, but we're also reheating it with the hot store. And eventually it goes to a power recovery unit, which is the discharge, which essentially is an air turbine. Or in other words, it's a regular turbine, but instead of steam going through it, now we have high pressure, hot air going through the turbine. And the exhaust of the turbine is basically atmospheric air. And because I'm trying to improve the round trip efficiency, I have to utilize the thermal store and the cold store as much as possible, because I have a charging component which does require auxiliary power. So before I go to the process video, right now, the current design is basically the round trip efficiency is between 50 to 60%. However, if I am locating this thing close to a facility where I have gas from a LNG plant or cold available from a process plant, I can utilize that to increase the cycle efficiency. Similarly, I can take waste heat from many power and steel industrial plants back into the process to increase the RTE. And the intent is, if these are available at different sites where if it can be sited, then I can increase my RTE close to 70 or 80+%, which is when it starts comparing to lithium ion, as Mr. Sen has mentioned. So the other thing I wanted to comment is in terms of response time. So the whole idea of grid stability with energy storage is fast action to the grid. And I will talk about some of the fundamentals of AC grid in a couple of slides later. But if you look at it, basically from a fully export position, we want from power export from 0 to 5 minutes, 5 to 10 minutes full dispatch capability in the standard mode of operation with very high ramp rates. If you look at the right-hand chart, when you are producing liquid, we need to charge the system. So essentially the minimum time you would require is about 10 to 15 minutes, at what point you already have the liquefier load. then the ramp is very quick. Now, if you have liquid already stored in tanks, then you look at the ramp rate, it's less than 3 minutes in order to get it to full load. So essentially, the concept is in order to have an energy storage that works to support the grid, ramp rates are very important, and these systems are designed to produce that. So what I'm going to do now is I'm going to show you a process video, and hopefully it comes across to at least give you an idea how the system works. Let me go to this. Back here. I believe I have to stop sharing and reshare if I'm not mistaken. 1 second. Okay. Now I'm going to share my screen. Okay, can you see this video screen?
Yes, sir.
Okay, fantastic. I'm going to play it now.
HiView's cryogenic energy storage system consists of 3 main components. A charging device, which uses off-peak or excess electricity to power an industrial liquefier which produces liquid air. An energy store, where liquid air is held in an insulated tank at low pressure. And the power recovery unit, where a gasified liquid air is used to drive a turbine and generate electricity. Operating efficiency is enhanced by adding a thermal store and our proprietary cold store. These capture and store waste, cold, and heat from the process. Here's how it works. Air is first cleaned and dried and then refrigerated through a series of compression and expansion stages until the air liquefies. This process is based on the Claude cycle, which is over 100 years old. The liquefied air is then stored in insulated tanks at low pressure. These tanks are readily available from the industrial gas industry or a very large-scale LNG sector. When power is required, liquid air is drawn from the tanks, pumped to high pressure, reheated and expanded. The resulting high-pressure gas is then used to drive expansion turbine generators. No fuel is burnt in the process, resulting in the exhaust producing clean, dry air. Waste cold from this stage is captured by the cold store. This is later recycled to enhance liquefaction efficiency. And in a similar way, heat generated from compression during recharge is captured by the thermal store. HiView Power, delivering tomorrow's storage with today's technology.
Okay, so I'm going to go back to my presentation now. Okay, share screen. Okay, very good. So so you looked at the process that identified how it works. Obviously, it's a very simplified what I'm sharing. There's a lot more engineering details that goes into it. But if you look at it, one of the key attributes of this is it's got a limited compact footprint. So if you look at this is a schematic of a 20 megawatts electric storage capability with 6-hour system would require about 1 acre of land. If you went to a 6-hour system providing up to 200 megawatts electric, now it will be configured to fit into a 5-acre site. So the whole idea behind this liquid air plant layout system is this is not limited to geographic location. Obviously, as I mentioned, if you can site it near a process or industry where you can use some heat and cold, it increases the cycle efficiency. But this plant can be built anywhere, next to a wind facility, next to a solar facility, and it's independent of site locations. Whereas if you look at the long duration energy storage today, like compressed air and hydro, they're also very, very site specific, as has been discussed in the past. So one of the key things is there's nothing exotic in this plant. If you look at it, most of the components can be commercially obtained from the power, oil, and gas sector. Liquefaction of gases has been happening well over 100 years, and this Claude process is an industrial liquefier that can really be readily bought. And then what Highview did is they built a pilot plant to look at the process and particularly look at the power recovery unit. This was done in UK, and it ran for several years, and basically to prove the process. And then they did a demonstration project at Heathrow Airport for 5 megawatts, 15 megawatt per hour, 3 hours. And this was utilizing nitrogen and then providing power to the grid, again, to further demonstrate the power recovery units. So what we're doing right now is there are several projects in development to large commercial scale where we're looking at 200 to 350 megawatt hour, 5-hour storage systems. That is basically going to prove the concept commercially. And that currently is in the works in several markets. So let's understand why this is important. Very quickly, if you understand the pillars of AC transmission, as Mr. Bishnoi has said, there's a huge impact to the current grid as you get more and more renewables. As India has a very aggressive renewable target, you are going to require a lot of work to stabilize the grid, because traditionally the grids have been utilizing inertia, which rotating turbines produce from conventional power. And if you look at the process, our system actually provides inertia back into the grid because now I have a synchronous generator that's providing dispatch power. So if you look at the AC grid, you need active power, you need reactive power, obviously the inertia, and short circuit power. So as discussed by the two previous gentlemen, there is enough opportunity for several modes of energy storage that will provide these services to the grid, or as we call them, ancillary services. And one of the key things, as Mr. Bishnoi has mentioned, is policy framework to enable IPPs, owners, and industry to be able to monetize and provide these services to the market. So bottom line is energy storage plan economics depends on the value of these services provided to the grid. And as you look at the advanced economies today, the most advanced market is the California ISO market in the US, where they actually have pricing schemes about total ancillary services and the amount of time and process required for providing the services as California puts more in wind. And I see the same situation happening across the globe. And if I'm not mistaken, the CEA in India has introduced a draft on ancillary services precisely for this reason as they look at more large storage duration. So let's talk about fit for the technology. As Mr. Sen, Dr. Sen had provided earlier with the battery storage and lithium-ion and flywheels, if you look at this chart, the x-axis goes to the gigawatt scale, and then the y-axis goes to the time duration. Currently in the world, reactive power, which is really what the lithium-ion batteries can do, they occupy between 10 to 100 megawatts. This is their sweet spot, and roughly 0 to 4 hours is what the current industry averages are. But if you look at a country like India, where you're going to be putting almost 100 gigawatts on the grid, you'll be at 120. And the Prime Minister of India's ambition is for India to have 430 gigawatts, which is significant. You will need gigawatt scale or larger storage. And for this, currently only two processes there, which is the compressed and pumped hydro. And now with this liquid air energy storage system, now I can make this into a gigawatt because all I need is extra tanks of liquid air oxygen storage and a power recovery unit with its ability for longer duration of dispatch. So essentially, we can now design a plant for not only 5 hours, 6 hours, 10 hours, but 24 around the clock. So if you look at it, the top of the chart is all the ancillary services that is required. And as Dr. Sen mentioned, the capacitors, flywheels, they're fast, short upset, local voltage, fast reserve. But as you go into longer duration storage, the grid requires significant amount of stability, which primarily is currently being provided by inertia. And our system provides inertia in addition to compressed air and hydro. So if you look at the top of the chart, the voltage, black start, frequency, all the way to grid shifting and grid capacity is being served. So we see this as a potential to offer hybrid energy systems. It could be with ion or batteries for short duration. And then as you go to long duration, this LAES, liquid energy storage, could be a solution. So again, if you look at what this offers to the industries, the gentleman previous to me talked about data centers. They're high power need. They need a lot of energy. So that could be a small supply systems for them. But if you look at power generators, they require fast ramping, time shifting, reactive and real power control, efficiency, utilization, and black start. Then you look at the transmission providers. They want congestion. They want demand management, as Mr. Bishoy mentioned. How do you address reactive power for voltage control? When you don't have lack of inertia, how do you take care of that for stability? And of course, losses and energy cost. Then you have the distributed providers that want to manage it better from how they distribute it. Again, they're looking for inertia, they're looking for stability control. And lastly is the industrial commercial facilities that are looking to decarbonize their footprint, whether it's mining companies, whether it's cement, whether it's steel mills, where they're looking to buy power from clean energy sources. So it could be, these could be done there. And also, importantly, industrial facilities could have waste, heat, and cold that can be utilized to increase the efficiency of this LAES system. So, I know it's a quick presentation, but the bottom line is the world will require significant amount of investment in order to meet the energy storage requirement. And we feel the LAES offers some benefits when it comes to long duration. One of the reasons this is a little bit beneficial is, one, these plants are designed at gigawatt scale or larger. There is no end of life degradation. So for example, if you're charging 50 megawatts, you're going to discharge 50 megawatts. And the difference is with lithium ion batteries, as Dr. Sen has mentioned, there's a depth of discharge issue, and you have to have a timeline where you need a replacement. So if you look at a large lithium ion plant over a 30-year life, you need at least 2 years worth of replacement of batteries, depending upon the life cycles and how much a depth of discharge. So there's a CapEx cost to it. So if you look at the LCOS cost of this gigawatt scale, we feel we can not only meet parity, we can actually lower the LCOS based on a 30-year life cycle. So again, it has a lot of benefits, but the key thing is, how do we price and monetize the ancillary services that these energy storage would offer in the grid? So again, real quickly, zero emissions, there's no CO2 being emitted. The emissions out of the turbine is atmospheric air. Right now, we're in the 50 to 60% efficiency. We are now trying to increase with process improvements to get it up to 70 or higher. Obviously, it's going to be based on LCOS. This can be built on anywhere. It's got zero water impact, and it can be symbiotic. It can be optimized with industrial applications to increase efficiency. So if you go to Highview Energy, they have a lot more information on this technology. And of course, we'll be offering a lot more detailed white paper on this as we are further developing this process, and of course, as projects get implemented. So that's what I want to, very high level for presentation on liquid air. Thank you.